Alright, so at this point we're going to talk a little bit about the concept of K sub A, something called the acid dissociation constant. It applies to weak acids. And there is a similar idea which is Kb for weak bases, but we're going to focus on Ka for now. You've seen this letter K before. It means an equilibrium expression. It means exactly the same thing here. The only difference is the sub A. Of course, the sub A is for acid. So, let's talk. Oh man, I feel like I'm about to sneeze. Don't you hate that? Bloody nose. Alright. The fact is that some acids are strong and some are weak. Let's see what strong acids we can think of. Well, let's see. Common strong acids: HCl, HBr, HNO3. Alright, so hydrochloric acid, hydrobromic acid, nitric acid, HClO4, perchloric acid, HI, hydroiodic acid. I think that's the correct pronunciation. And then the last one that everybody gets exposed to in their car, sort of, sulfuric acid. So what's the one common thing about these? Well, the only common thing is that they are strong acids. And what does that mean? Well, what does an acid do? Well, an acid dissociates. And what does an acid dissociate into? Well, it dissociates into its two constituents, one of which is H+, and then the conjugate base of the acid. If we were to use the example of HCl as an example, HCl, an aqueous solution of HCl, when it comes into contact with water, it does something. You know what? Well, I'll actually keep that up there. It does something very particular. The HCl dissociates into H+ and Cl-, and the H+ gets picked up by the water to form H3O+, the hydronium ion, and then Cl-. Okay. Now, this HCl is such a strong acid that it essentially dissociates. What do you think the next word's going to be? Well, the word is going to be completely. Maybe not exactly completely, but close enough. Essentially, 100%. So if we were to think about this in terms of an equilibrium, then the equilibrium position would be way over here. Alright? So much so that this is not really considered an equilibrium at all. This is essentially a one-way reaction. Because when this and this react, they give this, and nothing then happens. It doesn't go back the other way. And that is the case for all strong acids. That's one of the reasons, well, the main reason why they're so dangerous. Okay? Because this H3O+, if you have enough of it, this stuff will mess you up. And you could write out a similar equation like this for any of these 6 strong acids. All right. Now, weak acids, on the other hand, weak acids obviously don't dissociate completely. All right. Let's think of a common weak acid. Well, probably the most, one of the most common weak acid is acetic acid. Where would you find acetic acid? Well, if you're not sure, you'd find it in your kitchen or in your pantry. You put it on your chips, your fries in this country. In England, you put it on your chips, and you put it on your fish too. The main constituent in vinegar, outside of water. In fact, vinegar is approximately, I think it's about a 5% solution of acetic acid in water or something like that. Anyway, the formula for acetic acid is as follows, and you'll have seen this before. We have our hydrogen at the start of the formula that gives us the indication that it's an acid. And I will tell you, you will see acetic acid written a different way than this later on, but for right now we're just going to stick with this. And when we put that into water, We have exactly the same dissociation procedure, or the dissociation process that we had with the strong acid. So we get out H3O plus, and in this case the acetate ions, the acetic acid without the hydrogen there, C2H3O2 minus. But because this does not dissociate completely, we show this as an equilibrium. Alright, and this is the case for all weak acids. Only partial ionization or dissociation. And every acid dissociates to a different percentage, a different extent. So what this means is, in this solution of weak acid, you have a considerable amount of undissociated acid. In other words, acid that hasn't ionized or dissociated to give this. And so because of that, in any solution of weak acid, you're going to have a concentration of the H3O plus, of the conjugate base, and then of the acid, of the undissociated acid itself. All right, and you can show that by applying the law of mass action like you've done in your equilibrium chapter before. You'll say that K is equivalent to the concentration of your products. In this case, the conjugate acid and base of the reaction between acid and water, over the concentration of my acid, and then the concentration of water. Now there are a couple of things that I'm missing here. One of them is, because we're dealing specifically with the dissociation of an acid, this is K sub A rather than just K. You'll have seen K sub C before, K sub P, K sub EQ just to indicate equilibrium. K sub A refers specifically to an acid. Now there is one of these four species here that actually I should take out of this equilibrium expression. Now who knows which one that is? Well, it's the only one I can't measure the concentration of, and it's water. That's why you'll never find pure water as a species in an equilibrium expression for anything, because, like we've seen before, it's a pure liquid and you cannot measure its concentration. Okay, that makes sense so far? So let's just talk about what this actually means when we look at these two relative concentrations. If I have a very high concentration of my undissociated acid and a very low concentration of my ionized products, then what does that tell me about my value for Ka? Well, that tells me my value for Ka is low. And that's what it is for most, well, for virtually all weak acids. A lot more undissociated acid exists than does the dissociated products. Okay, so the trend is the lower the Ka value, then the further to the left exists the position of your equilibrium. The further to the right of your equilibrium, the higher the Ka. All right. So you'll find some weak acids have relatively high Kas, some have relatively low Kas. Alright, they're always going to be much lower than, even if you could generate Kas for these, which is really very difficult to do. Alright, so let me just give you a couple of ideas. But not a couple of ideas, a couple of examples. Hydrofluoric acid, which is an example of a weak acid, has a Ka of 3.5 times 10 to the negative 4. No units as before, this is just a ratio. Acetic acid, AA, I'm just going to shorten that. The Ka of acetic acid would be 1.8 times 10 to the negative 5. Alright? And then formic acid. Formic acid is just an acid with one carbon, the smallest acid around, and its formula is HCHO. O2, because I doubt you've seen that one before. Formic acid has a Ka of 1.8 times 10 to the negative 4. So here is one question before we move on to our last piece here. If I was to ask you which of these three has the equilibrium that lies furthest to the left, in other words, which acid is the least dissociated, it would be the one with the smallest Ka, which would be that for acetic acid. And then if I was to ask you which one has its equilibrium point lying furthest to the right, it would be the one with the biggest Ka, which in this case would be hydrofluoric acid. Alright? Okay, let's look at one more thing before we finish. And I'm just going to do a couple of things here. I'm going to write out two reactions. HCl plus H2O, just like we've seen before. That's H2O liquid. Going to H3O plus and Cl minus. And I'm going to do the same thing for a weak acid. HF, aqueous, plus H2O, liquid, works in exactly the same way, and we get out H3O plus. In this case we get out F minus, not Cl minus. Now the one thing I want to focus on right now is the concept of something called the conjugate acid and the conjugate base. Alright, so conjugate acid, conjugate base. I want to make sure I have them spelled right. Alright, and I'm just going to say Ca, so that I have to write the whole thing out several times, and then Cb. Let's look at the case where we have, oh, you know what, I've messed up here. Can anybody see where I've messed up? I messed up somewhere in my second equation here. This is actually in equilibrium. I have to show that other arrow, because I want you guys to see the concept of the conjugate acid and base is the same whether you're dealing with a strong acid or a weak acid. So whenever you have an acid and a base, HCl is a strong acid, so by definition water is the base that reacts with it. The conjugate acid is very simply the base after it's picked up the hydrogen from the acid. The conjugate base is what's left of the acid after it's given up its hydrogen. So if we had to define which of these is which, H3O plus looks most like the H2O after it's picked up a hydrogen, which is true. Alright, so the H3O plus is the conjugate acid. The Cl minus, therefore, is the conjugate base. Notice that the base, the original base, always gives the conjugate acid, and the conjugate base always comes from the original acid. Alright, so you'll always have the acid and the conjugate base as a pair, and then the base and the conjugate acid as a pair as well. So let's just do the same thing again. HF. Remember we said the Ka for HF was 3.5 times 10 to the negative 4. There's going to be a particular couple of situations where you're going to ask yourself, well, I don't know if this is the acid or the base, because this is a weak acid. Is water a stronger acid? Well, rather than just guessing, I can tell you that the Ka for water is essentially 1 times 10 to the negative 7. So it's clear to see that if you were to consider water as an acid, it's very, 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 very weak. Certainly this is a stronger acid. So therefore the HF is the acid, the water is the base. And if that's the case, if the water is the base, then the H3O plus is the conjugate acid, and the F minus is the conjugate base. And if we were to link these up the way we did before, the base always gives you the conjugate acid, and the acid always gives you the conjugate base. Alright, just one more thing about this. If I have a really, really, really strong acid what do you think that says about my conjugate base? If this is very strong, which HCl is, if it's a very strong acid, my conjugate base is just going to sit there and just sort of stare around and be happy. Alright, because this chloride is very happy to have given up its hydrogen, otherwise this wouldn't be a strong acid. So there's kind of an inverse relationship. If the conjugate acid is very strong, its conjugate base is very weak. Alright. Now HF is not very weak, but it's a weak acid. Relatively weak. Alright. Which means the conjugate base that comes from it is relatively strong. So what that means is, because this is a relatively strong base, it can grab the hydrogen from the H3O plus and take the equilibrium and take the reaction back the other way. Then the same happens and it goes back and forth and back and forth and back and forth and sets up the equilibrium. Doesn't happen here because this is very strong and this is very weak. Alright, and basically that's it. Alright, so that is a little bit about the concept of Ka and a little bit about conjugate acids and conjugate bases. Oh, you know what, one thing before I finish. When you're looking at conjugate acids and bases, you want to be able to predict which side the reaction is going to prefer if you're in an equilibrium. The side that's always going to be preferred in an equilibrium is the side that has the weak conjugate acid, or the weak acid and the weak base. Alright? So if we were just to look at this one right here, and we were to say, okay, HF is a relatively weak acid. Alright? H2O is a very weak base. So relatively, H3O plus is a relatively strong acid, at least compared to the HF. And F minus is a strong base compared to the H2O, which is very weak. Notice that both the weaks end up on the same side and the strongs end up on the same side, and this is pretty much always going to be the case. You're always going to have both your strongest base and your strongest acid, or whatever, on the same side, and then the weakest acid and weakest base on the same side as well. So in this case, where would the equilibrium be favoured? It would be favoured on the reactant side. All right. Okay, so that's all I want to talk about. So there you go. Thank you.